of them on management informatics and software technologies, computer science education, embedded software, IoT, and in particular, our research group works on data science information extraction. We develop methods to extract information from data as well as from images, specifically from remote sensing images. We are working in some clustering methods. Particularly, I work on extracting information from medical images. And more recently, we opened a neuroscience project that is related to behavioral, computational, and biological neuroscience. In particular, we are working on human routines behavior discovery in collaboration with the life logging and egocentric vision group of Universidad de Barcelona. The main research line is human routines discovery that is carried out by this team. Martin Menchon is the doctorate fellow of this team. He has a doctorate fellowship of CONICET, that is our funding institution for research in Argentina. Martin, as well as me, works on UNICEN. Petia Radeva works on Universidad de Barcelona, and Estefania Talavera in University of Twente, Netherlands. There are two secondary research lines. And the first one is cognitive teleneuroRehabilitation in collaboration with Hospital Italiano de Buenos Aires. We will talk very shortly about this later, as well as the third research line that is about posture monitoring for Parkinson patients. Okay, let's begin with human routine patterns. At first, we will try to think about why to analyze these human routine patterns. The first answer could be to understand the lifestyle of people, but that leads to another question, that is why we want to develop methods that automatically can understand the lifestyle of people. From the theoretical point of view, this is related to perceptual computing, that stands for understanding computing in terms of how is the human that is using, by example, a computer program. But in a more practical way, with this kind of human routine patterns discovery, we can answer questions like, how does my daily life look like? By example, and here you can see a graph that shows how the time is distributed between personal time, social time, and work time of a person that is using this technology since 6 months. Okay, so also this human routine pattern discovery can be helpful to monitoring health in everyday activities, as well as sport and recreational activities. It can be useful for monitoring patients, to assistance of elderly people, and by example, making some system that can give some warnings, but warnings that understand the person routine of the system, okay, that is used in the system. And this is very interesting for us in relation to the second research line for memory enhancement and rehabilitation, specifically the memory reminiscence therapy. By example, in here you can see available solution that was developed in Universidad de Barcelona group that can distinguish automatically pictures that were taken by the user from an egocentric point of view, that can be remembered by the user in the future or not, because the picture in this case, by example, is too general. This is very useful for implementing serious games in relation with memory reminiscence therapy. So after talking about why we want to analyze, we will see how to analyze human routine patterns. And the truth is that it depends on the nature of the data we have. At first, we need to know which information we have to then start to thinking about how to develop method to detect routine patterns. What we know is human routine pattern is a regularity in the activity. So that leads us to perform some kind of life logging to register these activities. And today, live logging can be carried out by a multiplicity of devices. Every year, new devices are appearing in the market. So we will see how we use specifically the cameras to perform live logging to then detect human routine patterns. So what about live logging today? Everyone knows that social media platforms perform some kind of live logging based at least on digital activity, and taking advantage of the big amount of users that they have that are producing content on a daily basis. That is very good to train CNN and so on. And also today there are some healthcare wearable devices like smart clothes and smart rings that can perform some kind of live logging, at least from the specific point of view of the purposes for which this product were manufactured. Okay, so regarding to live logging on images, today there are solutions that can perform some kind of live log from vehicle and surveillance images, as well as some augmented reality applications that are running information extraction algorithms in line on the production of images from these cameras, and in some cases even in real time. So let's talk about wearable cameras. That there are the cameras that are interesting to detect or to discover human routines from egocentric point of view. These wearable cameras are evolving year by year and are getting smaller. And some of them are product specific, like Google Glass, Snapchat Spectacles, some security cams, and the new ones that Facebook and Xiaomi have launched some weeks ago. But for us, it's interesting cameras like the narrative clip, because it's not too expensive and have a reasonable resolution and battery autonomy. And the more important thing is that you can use the images produced by these cameras to our own solution, not depending on any kind of products and so on. So the market of these kind of cameras is growing continuously, and as a consequence of this, is expected that the cost gets reduced, as well as the functionality get increased. Okay, so one very important aspect that we have to take into account is the ethical point of view. There are some ethical guidelines that talk not only about the capturing of the taking photograph regulations, but also on the manipulation on the images and on the extracted information from the images. And specifically, these guidelines treat perform an analysis of the anonymization, the confidentiality, the distribution of responsibilities of the team that will be manipulate the information. There are even some templates of legal contracts, and also the data encryption as well as data storage are covered with this kind of guidelines. Regarding the economical and technical feasibility, that seems not to be a problem in the future, because as a consequence of the growing of the market, is expected that the cost per gigabyte continue dropping, as well as the devices get cheaper and easier to use. Okay, one interesting thing of this is that the storage capacity is increasing very fast in comparison to our ability to extract information from the stored data. Even with the last advances in artificial intelligence, the speed of the image production is too fast. Okay, so we will see which is our motivation to perform this kind of human routine discovery. We try to do this to detect human routines from egocentric image for health and quality of life improvement purposes. Okay, So actually there are some solutions like activity recognition. By example, in this work, you can see how the images can be distinguished between the activity that are performing the user. In this case, the user is having an informal meeting. In this case, the user is traveling by a train or metro. Also, there are works that solve the social interaction characterizations. By example, in this work, a solution can automatically distinguish if you are having an interaction with a colleague, with the children, with friends, okay? And all the related works of these are the food scenes classifications that are able to identify which food you have in front, and even can infer the nutrients that this food is having, okay? So other works perform some kind of emotion or sentiment analysis. In this work of Talavera, you can see that a solution has separated this frame in relation to they have a positive sentiment, and this frame have neutral sentiment, and these have negative sentiments. Of course, this was evaluated by a user labeling. Okay, so from the technical point of view, the important thing in here is that these solutions involves some kind of short-term photo stream analysis. The challenge today is on long-term egocentric photo streams analysis, because it requires more effort. By example, when we try to process these long-term egocentric photo streams, we will have more images, we will have lower frequency, and as a consequence of this lower frequency, we will have a context information that will be sparser, and even we will have dynamic points of view even on the of the same objects, okay? So today, if you want to work in this, there are some available data sets like the NTCIR live log and the dataset from Universidad de Barcelona that is called Ego Routine and is available in this link. We have to say that still these datasets are limited in terms of the users and the number of users and the days they covering. And you can see here some examples of these 4 datasets. And of course, all of them are taken from an egocentric point of view, but they involve different objects, different places. The images were taken by different users, and this is not a problem, because when you try to develop a solution using these 4 data sets, you will have a more richer information. So let's go to talk about how to identify automatically this pattern for a user in an unsupervised way. It's very important, the unsupervised characteristic of this. If you get showed these photo streams that is for one user, that covers all the times of the day that the user have the camera working, and these are the days, okay? And every picture in here is a representative picture of a half an hour time slot. We visualize it like this because of the big number of images we have. So if you get asked visually to identify patterns, you can see, okay, I can identify in here that the person is working, and in here the person is in recreation time, is at the beach, etc. And these days also, this corresponding to this group of images, okay? And even you can identify sub-patterns and more image belonging to these patterns. But when you try to do this in an automatic way, it's not so simple, and we will see how was our approach to perform this. We decide to divide the process in 3 stages. The first one is about information extraction from the frames. The second one is to represent this information in a proper way. And the third one is about to analyze the data to extract patterns. So all this in an unsupervised way. And okay, so for the first step about which information we extract, for every frame or every image, we extract the appearing objects, the corresponding scene, and the activity that the user is carrying out. This was published last year, and we work with the 4 dataset that involves about 400,000 images that cover 315 days of 14 users. Okay, so how we detect the appearing objects. In our case, we have used several convolutional neural networks. ULO4 was the best performing one, but other object identification convolutional neural network can be employed for this. In our case, the scenes were detected by VGC16 places 365 convolutional neural network. This was fine-tuned to adjust the scenes and to reduce the amount of scenes that this network can detect to make more efficient the process. And the activities in our case were identified using a convolutional neural network that was specifically developed for this in Universidad de Barcelona group. So with these 3 convolutional neural network and given a frame, you can say, okay, in this frame there are a cap, there are the following objects: a cap, a TV or monitor, a person, a keyboard, and of course more objects that are not shown here. Here are only the ones that have the bigger probabilities. The activity that the user is carrying out is working, the scene is an office, and with this information, we go to the second step that is about to represent it. We choose several representations, but the graph representation maybe was the best suitable for us. We built a directed graph in which each node corresponds to a time slot or half an hour, by example. And every node is characterized by the concept that the pictures of this node have, by example, the scenes, the activities, and the objects, okay? So we also develop some kind of distance to compare 2 nodes. And this distance function was based on the object, the activities, and scenes that are present in 2 nodes to compare the dissimilarity between them. Okay, so with these elements, we perform a multidimensional scaling that helps to show us the nodes of the graph and how they were separated, and you can start to see some semantic similarity or dissimilarity, okay, between the nodes of the graph. But the more interesting thing is how we analyze this information, that the step 3, to find patterns. So we choose to follow a strategy of aggregating similar time slots, designing a greedy heuristic algorithm that given all the photo stream of a user of all the days that the user wear the camera, and start with a seed that have some specific characteristic, and from this seed we start visiting contiguous time slots and from contiguous days, and also we visit time slots that are similar in terms of the distance, but are not in contiguous days. Okay, so with this we can put together the time slots that are similar, but we have to decide when a cluster is finished and when a second one begins. So in our case, we decided to measure some metrics like entropy, the first derivative, the second derivative, and so on, and establish a threshold to decide when the first cluster ends and when the next cluster begins. So in this case, you can see that second derivative, when the second derivative is 0, a cluster is considered finished and begins the new one. And you can see that at the right, the patterns, the time slot that were added, okay, that corresponding to nodes of the graph, they have some similarity. All these nodes of the graphs corresponds to the first cluster in our case. Okay, so 2 example detected patterns from this method are these. The first one cover these 4 days in this time slot is when the user is at the office carrying out these activities and surrounded by these objects. And the second one is in places like transportation, pathways, okay? And the user is making these activities and cover more days in these time slots. Okay, so with this solution, now we give this photo stream of a given user, and the solution can say, okay, here are the patterns that I found. You can see here that are patterns that are similar to the ones that we tried to identify visually before, okay? So recreation in here and working in here. And you can see other patterns that have been found for this method. So how is the evaluation? We choose to evaluate this solution from the quantitative point of view through a representative metric that is a measure that considers the amount of data the pattern covers, the amount of images, the total time, the repetition, and other parameters. Also, we have an evaluation through clustering metrics like silhouette and Dan index and others. And we compare our solution with in this case, with 2 methods. The first one is ORTIS, that is a very similar method in terms of the objectives. And DBSCAN is a clustering method that is a general method, but is a reference in this kind of problems. And our solution perform better from the silhouette point of view. And also we perform a qualitative evaluation through general surveys. We will see now in which consist these surveys. The surveys are composed by several questions that the user of the surveys answer, and 73.6 answered that our method detected better clusters. So, and also we perform a qualitative validation through user labeling. So the conclusions for this research line is that we developed a method for discover human routine based on finding repetition, pattern of object, activities, and scene. We consider that this work is the beginning of the research line to discover meaningful patterns of human behavior. The future lines of work is to evaluate this method with a bigger number of users, compare with another clustering methods and to another potential routine discovery method that can appear in the future, to incorporate extra information like GPS and so on, and also to perform a deeper evaluation of subset of descriptors by example analyzing the frequency of the objects and the evaluation of a semantic similarity of recognized objects. Okay. I will comment very shortly the last 2 results of research lines. The second one was a cognitive teleneuroRehabilitation. This was made in collaboration with Hospital Italiano de Buenos Aires. And we have developed some exercises that are running in a web platform for cognitive, visual, spatial, and episodic memory oriented rehabilitation. Okay, so over these exercises, we perform some kind of patient event logging and gaze tracking. And this gaze tracking allow us to detect if the patient is looking at the figure or not. And we, by this, can measure time delays that help a physician to diagnose better, because they have information of the delay between the figure appears on the screen, the user locates the figure with his gaze, and the delay between the user locate the figure and the user clicks or touch the screen over the figure. And now we are planning to also to to implement some motion detection that can improve the available diagnosis information. So that's all for the second research line. And the last one is a posture monitoring for Parkinson patients. It's related to a problem that is based on a neurological originated abnormal posture that is called camptocormia. And today's solutions are based on devices that measure, analyze, give some alert, and there are some products on the market. Some of them are general purposes, not specific to this disease. And our approach was to build a prototype based on the 32 bits ARM chip. And the novelty is it have a vibratory alarm instead of audio alarm or an electrical alarm like ecstasy. And our idea is to make this product low cost and open source from the hardware and software point of view. And now we are planning to begin the test, the validation of this device. So that was all. Here are the references, and thank you very much for your attention. I will be a pleasure to answer any question.
Thank you for your attention. Thank you for an interesting talk. We have a time for a few short questions. Let me just have one brief question. These computations, this image processing that you perform on the image, can it be done inside this wearable device that take this image as of today, and maybe will it be possible in the near future?
I think it will be possible because the part that can be embedded in some device is the part when you using the neural network, and not the part when you train the neural network. So maybe a hybrid solution is better when you train on a server, but you have your solution running on a wearable device. This is possible.
Thank you. No. We also have a question in the chat, and the question is the following. Do you use only visual data, or also some neural interfaces are also used?
No, only we try to use visual data. Now we are starting to add in more information, but we started to add in GPS information and some wearables devices information, like the devices for health monitoring. Not yet some kind of brain interface or something like that. Not yet.
Thank you. Do we have any other questions? If not, let us proceed to the next talk. And the next speaker is Professor Liam O'Fowlane from Ireland. He's a leader of the Nanophotonics group at the Center for Advanced Photonics and Process Analysis, which is at the Munster Technological University and Tyndall National Institute. Professor O'Fowlane will present the talk, Integrated Photonics for Advanced Indirect Spectroscopy.
Good afternoon. Do you hear me?
Yes, we can hear you.
Perfect. Thank you very much for the invitation and for giving me the opportunity to speak at your conference. It is a shame that I'm not there in person. It would have been great to visit again, but we just need to do with what we can, with what we have. So, right, I'm going to share my screen. You see presentation mode?
Yes, we can see the presentation.
Just give me one moment to adjust to Windows. Right. Okay. So, yep. Today I'll give you my talk on advanced photonic integrations for optical sensing and indirect spectroscopy, and I'm representing the Center for Advanced Photonics and Process Analysis of Munster Technological University. So to give an outline of my talk, I will start off with an overview, just explaining the importance of optical sensing and spectroscopy. Then I'll move on to the device side, the nanophotonics and photonic integration, and its potential role in the wider field. Then I'll move on to the technique of refractive index sensing as a means of detecting various compounds, and finish up with indirect spectroscopy and some outlooks for this new area. To begin with, just a quick overview for photonic sensors have a number of advantages for sensing and process monitoring. They have the potential to evaluate samples in situ, online in a factory, in a process line, or directly direct at the water side if you're environmental sensing, and so on. You get direct information on the molecules. It can be a direct and quantitative and qualitative analysis. There is no need for chemical consumables. You can get your answer direct from the optics. There's no chemical preparation in many cases. The technique is also very stable and can operate with minimal calibration, which is very important for field use. But you can see that the various fields or various areas are growing very strongly, and this is becoming it has been and it's continuing to be a very important area. And in some ways, there is it also supports growth in other sectors. That the optical sensors used facilitate quality control, compliance with regulation, and it was an important and indirect influence in those areas. For example, in pharmaceuticals, optical spectroscopy can be used to look at the active pharmaceutical ingredients, provide quality control, can be a faster, quicker technique with less operator time involved. Increasingly, it's being moved from the lab. So basically, where samples are taken from the process, from the factory, sent somewhere for analysis. Increasingly, the optical tools are coming to the factory to be used in line, giving instantaneous feedback on what's happening in your production. And for example, this will facilitate a transition from batch production to continuous production, which means the amount of the amount of chemicals or the reaction chamber volumes can be reduced with considerable savings in terms of costs and improvements in performance. Another important area is there's an increasing need for certification and high quality data. So, for example, for environmental monitoring, it's key that the measurement, that the answer that's produced is reliable. There's been, I'm aware of some recent press reports of data that comes from bad sensors that have created scares amongst the public. So it's vital, or the environmental protection agencies hate those sort of scare stories. So in general, the environmental protection agencies of the various countries only want to see sensors that are certifiable, that have been proven to be calibrated and reliable. And this is one of the strengths of many optical sensors, as opposed to some of the other techniques that are available. That the data, but in short, data produced by an optical sensor can stand up in court. Equally, when it comes to process monitoring in a factory, you want to be sure that the information you're getting and making decisions on is good. Challenge, of course, are cost. Lasers, current optical spectroscopy systems in existence tend to be large and complex. Here we see some examples. So in general, the absorption, let's say if it's environmental monitoring, when you're looking for pollutant gases, the absorption tends to be weak, which means that you need to beat the laser, the light needs to interact, or you need to pack lengths of meters in order to get a appreciable absorption, which you see on the top right. My mouse cursor on. Top right is a sample example measurement system that this sample cell can in very cases be many meters in length. Here we see a lab-based tool in the middle, and on the right is the type of sensors you see at airports and weather stations and so on. They all need to be very carefully controlled units. Temperature, humidity needs to be exactly controlled. So there's a clear need for smaller, more robust and compact sensors. And so that brings us to photonic integration. we're all very well aware of the electronic integrated circuit and the revolutions it's created over the past decades. Pretty much everywhere we go, we see we see chips of this style, boards of this style with a wide range of components on those boards. These components, transistors, resistors, capacitors, are linked together by wires. The Photonic Integrated Circuit is a newer device. It's probably somewhere between 10 and 20 years old, and is showing rapid progress, but we still have a long way to go before we catch up with electronics. So if we see an example on the bottom left, where we see lasers, photodetectors, lenses, all connected together by optical waveguides instead of wires. The component count is every year. There's more and more optical components are being put on chips, and the growth is strong. And one of the particular advantages is the strategy of the Photonic Integrated Circuit community is to leverage the development effort that has been made by electronics. So again, there's been decades of work have gone into creating semiconductor processing tools, equipment, furnaces, and the clean rooms by which in which these devices can be made with high precision. And the Photonic Integrated Circuit community tries to adapt, or we try to adapt ourselves to the tools that are available, that are tried and tested and reliable as much as possible. So here we see a few examples. So again, if you're aware of electronics, a transistor is made up of many different layers of silicon, metals, oxides, nitrides, and so on. And we try and do we use in general a simplified subset of what's required to make a transistor. But here we see some examples of patterned silicon nitride, patterned silicon. Bottom right, we see a modulator from Graham Reed's group in Southampton, where we see quite a complex array of electrodes required to drive this modulator at high speed. The good news from the optical device designer point of view is precision available is fantastic. That both the array of processes, the material quality is excellent. The electronics industry have done a whole load of hard work for us, and the purity of the materials is fantastic, and that allows us to make some very powerful devices. So here we see an example from a project we were involved with ST Microelectronics. In this particular device, it was fabricated on a 300 millimeter diameter silicon wafer. We were creating arrays or large numbers of distributed Bragg reflectors across the chip, which we see on the top right, or we see an optical image on the top right, and a scanning electron microscope on the bottom right. Again, we're leveraging the control that ST Microelectronics have on their fabrication processes. And here we see some of the optical characterization results from that chip. Again, we tested a substantial number of devices across that wafer, and we can see the plotting the center wavelength of the stop band of each DBR of the different devices. So we see that there's 4 different device types there, and we can see for each one we have a roughly standard deviation of just greater than 2 nanometers, or a little bit more than 2 nanometers for the different device types across the wafer, which is actually an incredible level of control. If you do the sums, if that 2 nanometer variation in wavelength corresponds to a 1 nanometer control in feature size across that wafer, which is a testament to the high standard of the fabrication processes available. And indeed, that's now very important for the designer, because if we know that that level of precision allows you to make very precise and advanced devices. Now, to move on to refractive index sensing, I'll start off with a little bit of background. So in general, most optical devices, or many optical devices, are sensitive to the refractive index of the cladding material. So here we see an example of what's known as a micro ring resonator on the top right. If the material of the immediately above the ring resonator changes slightly, the resonance wavelength of the resonator will shift. And this provides a means of monitoring what that material is that's surrounding the ring resonator. So here we see the a generic example of the shift in spectral position versus refractive index change. It is generally a linear relationship, which can be connected or you can connect the wavelength shift to the refractive index shift by this formula, where the eta is an efficiency factor. One of the key numbers that denote how good an optical sensing device is. First one is the sensitivity. It's basically the slope of the line we see here. So the more sensitive device, the bigger the wavelength shift for a given change in refractive index. And just important as well is basically the how well you can resolve a shift, which is basically the Rayleigh criteria that you might be familiar from astronomy. And this is proportional to the sensitivity over here times the Q factor of the resonator. So in short, the higher your Q factor, the better your optical sensor, your refractive index sensor. The higher the sensitivity, the better your refractive index sensor. And your detection limit, the smallest quantity you can change, is inversely proportional to this figure of merit. Here we see some examples of an early refractive index sensor work that I was involved with a colleague of mine, Andrea De Falco. In this case here, rather than using a ring resonator, we used what's known as a slotted photonic crystal. And here we see some experimental changes in the spectra as different fluids are passed above the substance. Now, a disadvantage of refractive index sensing is that it is, many substances change the refractive index. So if you want to be specific, the technique is to apply a technique known as functionalization of the surface of the sensor. And that is used by a set of chemical processes. The surface is cleaned, and then the Aptes chemical is applied to the surface. And then a suitable antibody, if you're looking for a particular molecule or particular substance, you attach the appropriate antibody to the top, the appropriate binding agent to the top surface, which will then attach itself very specifically to avidin, to biofin in this case, to avidin in this case. And then as these layers bind, if you're looking for avidin, in the first case, as we shift between this state here to this state here, the refractive index above the sensor changes, changing the resonance wavelength. And here we see some example results from my colleague Andrea De Falco. In this case, he attached a microfluidic channel to the photonic crystal to make it easier to use. In this case, as you're flowing different concentrations of sample above the chip, we see a shift in the cavity wavelength, which then is proportional to the concentration of the avidin in the sample. So that's an increasingly popular technique. There's been quite a number of research groups and companies have made experiments of this type. Now we're moving on to a new design that we've recently developed, which is based on a new type of photonic crystal. In this case, a silicon nitride photonic crystal. There are a few reasons for this shift. Again, we're actually looking, our ultimate goal is to make a more sensitive refractive index sensor, and one that can be incorporated into a laser for reasons which will become clear later on. So this is what we're calling a nanostick, which is a name my students find for this device. So it's we have light coupling in through the waveguide here. Schematically, we see below we see light coupling into this device, into the one-dimensional photonic crystal. Oops, wrong direction. It then couples back out, and on resonance with the cavity, light couples in, couples back out, giving you a very narrow reflection spectrum, and some light is scattered, of course. And we see in transmission, you see a sharp dip in transmission, and in reflection, we see a sharp pronounced peak in reflection as well. So, and if you go through the equations, you can work out the reflectivity and transmission coefficients based on some characteristic Q factors of the design. There's a few different flavors of this design. So the simplest is to have basically a one-dimensional photonic crystal with a constant width. This is not a very good design. It's relatively high loss. Your Q factors only about in the range of 10,000. Linear variation, it gives a substantial factor of 10 increase, but the actual cubic and quadratic variations in this varying the width of each element of the photonic crystal turns out to be the best design. This follows if you're a photonic crystal expert, it follows the principle of gentle confinement implemented by Professor Nola. Basically, the idea is to abrupt transitions between the optical mode and surroundings are bad. So you want to taper that. Ideally, you want a Gaussian mode distribution inside the cavity. And also add as well is these are basically a heart. They are a Fabry-Perot cavity, even though they don't really look like the traditional Fabry-Perot cavity at all. Light is confined in the center region, and you can imagine these sections to the right and left as being the mirrors of a traditional Fabry-Perot cavity. But yeah, despite the difference in appearance, most of the normal rules of a Fabry-Perot cavity hold. Here we see some of the results on wavelengths. If you can tune your wavelength by tuning the period or the separation between each element of the grating. Here we see some simulation results. This is the formula we used to implement the tapering of each element of the photonic crystal cavity. We're working with silicon nitride material on silicon dioxide. Silicon nitride has a number of advantages relative to other materials such as silicon. Silicon nitride has a very large transparency range and it is also a reduced thermal optic coefficient compared to silicon and other say 3-5 semiconductors, which is an important advantage for a sensor. You get better stability. And here we see some example mode profiles in the device for different photonic crystals in general. They work best when the refractive index above and below are symmetric. When this reduces optical losses, it minimizes the coupling between the TE and TM modes. Now, if you think about it, this is instantly a problem when you want to make a refractive index sensor because you want to have different substances above and below. And in fact, the traditional photonic crystal designs are not so good in this regard. That asymmetry rapidly increases the loss. But basically, you break the symmetry, which creates coupling into lossy modes. So we've implemented a new approach. Somewhat surprising approach is where we deliberately introduce an angle onto our photonic crystal structures. Traditionally, the rule is simple: you make your walls as vertical as possible, and many people have put huge amounts of work into optimizing their fabrication processes. But we realized that in fact this is not optimum. That the old approach is not optimum for a refractive index sensor with asymmetric cladding, and that if you you can see the effects here. So red is the perfectly vertical sidewall of each element of the photonic crystal. Due to the when the refractive index is not the same as the lower material, we see the Q factor, simulated Q factor, dropping very rapidly. In green, we see a 5-degree angle, and blue we see a 7-degree angle, and that shifts the optimum over and makes it actually considerably better as a refractive index sensor, or keeps the Q factor high, which, as I mentioned earlier, is one of your key concerns. I'll just blow that up again. So, so for the sensor we're looking at here for water cladding, the green curve here, this angle of 5 degrees is optimum. A little behind schedule, so I'll move here. This is some further simulations. So we went back basically to our old fabrication recipes and found one that would give us the desired 7-degree angle, and we fabricated a set of devices based on that principle. So here we see the experimental results. So if we made a series of devices, some that were basically the silicon nitride structure with air cladding, some with spin on glass, which we use at the moment, is a refractive index of about 1.4 or a little less as in these measurements. We can see that for the air cladding, we get a relatively low Q factor due to the asymmetry, whereas when we have a 7-degree angle, we get a substantial increase in the Q factor, thanks to this thanks to this effect, which cancels out or which suppresses some of the coupling created by the asymmetry. In the case of the spin on glass, has a close refractive index to the substrate, and we see no real change between the two. So this is an important step forward. And now, as here we see some results when we use this as a refractive index sensor. In this case, in these initial measurements, we are using water and a salt solution as a proof of principle, and we see the roughly linear change in resonance wavelength with salt concentration, and we can plot this as a sensitivity, as in nanometers of resonance shift per refractive index unit of change over here on the right. And we see in blue we have the simulated calculated numbers. In red we have the experimental. We see a relatively small difference, 180 nanometers per RIU as opposed to 220, which we attribute to the fact that the water may not be, or the solution may not be completely filling the gaps between the elements of the photonic crystal. But that's a big step forward. Now we take our next step, which is to build the photonic crystal into a laser cavity. So in this case here we see a generic a laser cavity. If you consists of 2 mirrors that set up the optical resonator with a gain element in between. In our case, we use a reflective semiconductor optical amplifier. The optical amplifier section provides the gain, and there's a high reflection coating that acts as the leftmost mirror. And then our silicon nitride photonic crystal provides the other mirror of the device. And we design the mode areas and so on quite carefully so that they match up. We'll see a schematic of the laser on the top right here. And in general, the base performance of the laser is quite good. We see a very narrow line with it, as we expect, as you want to see from a laser. Threshold currents are 10 to 30 milliamps, and we have power outputs up to about 10, or just short of 10 milliwatts at a current of 10 milliamps. And now we can immerse the photonic crystal in the fluid of interest, and we see a shift in the laser wavelength depending on whether we have in black here. So as if it's clad in air, we have a resonance of just 1530 nanometers. When the water, let's say when water is placed on the chip, it shifts the resonance of the photonic crystal over, which then shifts the lasing wavelength of the device over as well, which gives a very good sensitivity. In fact, we believe this is the first demonstration of a laser of its kind that we have a hybrid laser with a good output power that is sensitive to the cladding refractive index. If you have a traditional indium phosphide-based laser, the outside refractive index has almost no influence on its output power. There are some pure indium phosphide-based photonic crystals which would be sensitive to refractive index, but they typically produce nanowatts or microwatts of output power. So this is a first of its kind. And importantly, as I mentioned, the line of the laser is about 5 megahertz, which if you look at the equivalent Q factor is 10 to the 7. So we see huge improvements in this figure of merit, which we will be using to implement very high performance refractive index sensors. So I think I'm running a little bit behind schedule, so I'll skip through this section on integration, which we're developing a process based on what's known as micro transfer printing with Brian Corbett at the Tyndall National Institute. This is potentially an approach that gives that allows to integrate lasers or gate elements onto silicon wafers at the wafer scale, providing a very low cost total system. If you're interested, you can find more details in this publication here, or ask me questions later on. Next, let's move on to the final section of my talk, which is on on the outlook for what's known as indirect spectroscopy. So, as a reminder, spectroscopy is the mid-infrared range is a very useful regime for the analysis of a wide range of compounds. It allows, in this range, you can access the vibrational and rotational modes of different molecules which gives you basically energy levels in the 400 to 200 inverse centimeter range. Raman spectroscopy probes the same energy bonds, but requires a very high power laser, whereas mid-infrared generally uses a more normal laser with more normal output power. And there's been lots of recent developments in quantum cascade, interband cascade lasers, which are increasing the wavelength coverage and is driving a huge amount of growth in the in mid-infrared spectroscopy. Here we see some examples that different compounds have different absorption lines, basically different energy different vibrational modes of their molecules, and this is an excellent way of detecting a fingerprint of a given compound, which is useful environmental monitoring, process monitoring, and so on. So the traditional approaches is what's known as direct spectroscopy. We are currently working in 2 new projects. We're working what was described as indirect spectroscopy, which is a way of detecting the absorption of light without actually using a photodetector. So the technique is that you have a laser which you modulate. If the gas then is excited, if the absorption line of the gas matches that of the laser, then you will have absorption of the laser light by the gas, which results in heating. And as the laser is modulated, you have a transient heating of the gas. That transient heating creates an acoustic wave, which then can be detected using a microphone, hence the name indirect spectroscopy. It has a number of advantages. It can be very sensitive compared to laser absorption spectroscopy. If you remember, I mentioned at the start that very often you need path lengths of many meters, whereas indirect spectroscopy can be a much smaller device. And this is one of the early implementations of this. Use a chopper to chop the laser beam with a microphone to listen for this sound wave that's created. My colleagues, Vincenzo Spagnolo at the Polytechnic of Bari, have developed are the experts on a new approach, which is known as quartz-enhanced photoacoustic spectroscopy. In this case, the laser beam is directed between the prongs of the tuning fork. When the acoustic wave is being generated, you excite the piezoelectric active mode of the fork, and you generate a voltage when gas is being absorbed, which you see in this little unit here. Again, incredibly powerful technique as you can see, we reduced the system size down to a few centimeters by a few centimeters in size, as opposed to the many meters required in other systems. And there's been some very, very good techniques used. And now in a recent startup project, we're working with Vincenzo's group on using the techniques, photonic integration techniques, to make a more robust or make more advanced laser chips for coupling with his quartz enhanced photoacoustic spectroscopy techniques, where we'll basically both integrate the laser on silicon chips and combine them with the tuning forks to create a system that will be lightweight and robust enough to be carried on a relatively small drone, which with the applications in pollution monitoring, and now there is also another flavor of indirect spectroscopy, which is known as photothermal spectroscopy. The basic principles are the same. Modulated laser beam excites the gas, which results in heating. But in this case, the heating creates a thermal wave, which then creates a change in the refractive index. And my collaborator Bernard Lendl at the Technical University of Vienna is an expert in this technique, where he uses a high finesse Fabry-Perot cavity to monitor this change refractive index. Again, he has a probe laser at the inflection point of the resonance of the Fabry-Perot. As the refractive index change shifts back and forth, modulating or creating a change in the signal of the laser, which is then read out. Here we see one of his existing setups, and now in the Optify project, we are going to be combining, or we'll be building an alternative to this, where we use the tools of photonic integration circuits to use the refractive index sensors I showed earlier in my talk, combine that to make a very small, compact photothermal spectroscopy system. And one other point I'd like to stress as well is for both in indirect spectroscopy, the measured signal scales inversely proportional to the volume. So the smaller your sensing area, the stronger your signal. It's somewhat unusual in that regard. And so there's huge advantages to making more integrated solutions. So with that, I will conclude. As I mentioned, photonic integration is becoming a very important technology, which is enabling new types of sensors, photonic crystal lasers, and the connection of photonic integrations and silicon fabrication, coupling that to spectroscopy is very new, which is creating a host of new opportunities and application areas, which will basically give economies of scale and increase mass, or reduce the mass manufacturing, reduce the system cost, and we'll see a rollout of a very wide number, or more and more high performance optical sensors in the coming years. And I will thank my various contributors and funding bodies. Thank you very much.
Thank you. This is a very interesting talk. I have a little question. You have a slide where different size variation laws for Bragg ratings was considered: linear, quadratic, cubic variation. Is there any theory behind it, this explaining why one variation law is better than the other, or it's just the numerical simulation?
There's a theory behind it. It is so the Bragg rating. If you have an untapered Bragg rating, it'll just reflect. If you taper it, you create a cavity. Basically, there'll be a mode supported in the middle of the structure. And again, there's a lot of literature in the photonic crystal literature. There's a lot of photonic crystal literature on the best way of designing these. The principle is you would like to have a Gaussian shaped mode in the middle. If you had, let's say if you have a bad design and your mode with a top hat function, that will create lots of loss. So in fact, you want to design your structure to a very smoothly varying mode profile, And so that's the origin of the quadratic law. I'm not sure why the cubic isn't better, but the quadratic one is best. Maybe that answers your question.
Thank you. Do we have any other questions? Please, Evgeny Bezus.
Thank you for an interesting talk, Professor Rafael. I've got a related question to the previous one. Actually, one of the parameters is the law of the change of the width of this ridges of this grating. But another one, obviously, is the speed of the change, or in other words, the total size. Could you comment on this? Maybe I missed it.
Oh, yes. Yes, I probably forgot to mention that the total length is maybe about 40 to 50 microns. And that would be largely given by the refractive index contrast. So the larger the refractive index contrast, the less periods you need. In this case, we're using silicon nitride. Silicon nitride has a refractive index of a little bit less than 2. So if you're going from water, it's 1.3, to air, it's 1, obviously. We found basically, I think it's roughly 60 or so periods to be the optimum, to be a good trade-off between size and losses and Q factor.
Thank you.
Do we have any other questions? If not, I would like to thank our speakers again and thank for all the participants of today's session. Goodbye.
Yep, thank you very much.
Thank you.